So, in today's class, we will talk about our transformation matrix derivation for transforms DCT, Walsh-Hadamard for order of n equal to 2 and order n equal to 4. In our previous class, we talked about DCT, which was the discrete cosine transform, where our kernel, which I am representing by H, I have written it as alpha of u into alpha of v into cos of 2x plus 1 pi u by 2n into cos of 2y plus 1 pi y by 2n. Right? So, from this is a 2D function. So, we have shown that h of x comma y uv can be represented as 1D multiplication functions. So, I can write the same equation as alpha of u into cos of 2x plus 1 pi u by 2n into alpha of v into cos of 2y plus 1 pi y by 2n. Right? So, this is one function and this is the second function. So, if I represent the functions as a and b, then I can represent my 2D DCT function as multiplication of a into b. Right? So, that is why we call the DCT function as separable. We call it as separable functions. Now, we all seen that if input image is, say, suppose u, then my output transform function, which is v, output image, v is the output image, I can represent it by a multiplied by u multiplied by a transpose. So, we have seen that our output image v can be obtained from the u by doing transformations where a is the 1D function of the DCT transform function and a transpose. So, here we can see that the output transform function is given by this formula. Because the DCT is separable, we can write our output transform function as this form. Now let's calculate the DCT kernel of order equal to 2. When I say that order is equal to 2, which means that capital N is equal to 2. We all know that when N is equal to 2, X, Y, U, V values range from 0, 1 to so on capital N minus 1. So, Y also ranges from 0, 1, so on capital N minus 1. U ranges from 0, 1, so on capital N minus 1. V also ranges from 0, so on capital N minus 1, which implies that X, Y, U, V values are 0 and 1. Right? Now, let's calculate the matrix A, which I have seen in the previous slide. So, we have A is equal to alpha of u into cos 2x plus 1 pi u by 2n. Right? So, this is the other way of representing the matrix A is h of x comma u. Right? Now, we have x is ranging from 0 to 1 and u is ranging from value 0 and 1. So, the possible combinations of the coefficient matrices that we have to calculate are h of 0 comma 0, h of 0 comma 1, h of 1 comma 0, h of 1 comma 1. right? So we have to calculate the coefficients which are represented by h of 0 comma 0, h of 0 comma 1, h of 1 comma 0, h11. So we will substitute the values of x and y in this equation and we will get the values. So let's do that. H of 0 comma 0, which is equal to alpha of 0 into cos of 2x plus, sorry, x here is 0, so 2x plus 1 into pi into 0 by 2 into 2. So we get the value as alpha of 0 into cos of 0. We all know that if alpha u is equal to 1 by square root of n when u is equal to 0 and square root of 2 by n for u not equal to 0. So we will substitute the value of alpha of u in this equation. So we get the value as 1 by square root of 2. Right? So we get the values as 1 by square root of t. Now let's continue with h of 0 comma 1. So we get the value as alpha of 1 into cos of 2 into 0 plus 1 into pi of into 1 by 2 into 2, which we get it as alpha of 1 into cos of, this will turn up to be 1, this is 1, so pi by 4. Right? Now h of 1 comma 0, which will come up to alpha of 0 into cos of 2 into x is 1 here plus 1 whole multiplied by pi into 0 by 2 into 2. So this will turn up to alpha of 0 into cos of 0, which is 1 by square root of 2. So h of 1 comma 1 is given by alpha of 1 cos of 2 into 1 plus 1 into alpha of 1 by 2 into 2, which will turn up to be alpha of 1 into cos of 3 pi by 4, which is equal to minus 1 by, which alpha of 1 is equal to 1 by square root of 2 into cos of 3 pi minus, that is equal to 1 by square root of 2, so that is 1 by half. Right? So we have calculated the matrix h x comma u by using the DCT formulas as shown like this. Yes. Now, if say suppose I have my image as 1, 2, 3, 4, then if I have, this is my input image, this is my input image. So if I want to calculate my output image, which is DCT transformed, which is DCT transform function, then we get the output transform function V as A F into A transpose. So we have got our A from our previous thing as 1 by square root of 2, 1 by square root of 2, 1 by square root of 2 minus 1 by 2, which is we are multiplying it by 1, 2, 3, 4, which is our image, and the A transpose, which is given by 1 by square root of 2, 1 by square root of 2, 1 by square root of 2 minus 1 by 2. Right? So we do the proper matrix multiplication as shown here. So we get here as the output transform function as 1 plus 3 by square root of 2 and the other 2 by 4 by square root of 2 and 1 plus 3 by square root of 2 and the other 2 minus 4 by square root of 2 into 1 by square root of 2, 1 by square root of 2, 1 by square root of 2 minus 1 by 2. right? So we get the values as 4 by square root of 2, 6 by square root of 2, 4 by square root of 2, minus 2 by square root of 2, which we are multiplying by the transform function of the A matrix or the coefficient matrix. So this will give us my output transform function. So if we go for DCT kernel of order 4, here the n value is 4. So which will imply that x values will range from 0, 1, 2, 3. Right? Even the v values, the u values will range from 0, 1, 2, 3. Right? Y values will range from 0, 1, 2, 3. V values range from 0, 1, 2, 3. So similarly, like how in our previous of order 2, we have calculated, we can calculate the transform function, which will turn up to the equations. We get the coefficient matrix of fourth order as 0 0.5, 0 0.5, 0 0.5, 0 0.5. Then the next row is 0 0.65, 0 0.26, 0 0.26 minus 0 0.65. Then 0 0.5, 0 0.5, which is negative, minus 0 0.5, 0 0.5, 0 0.26 minus 0.65 minus 0.65 minus 0.26. So this is the DCT function or DCT transform function of order 4. So if we assume, if we can observe here, the matrix is as well is separable as well as it is symmetric. We can always see here that A inverse is equal to the A transpose of the complex conjugate. So it is also a unitary matrix. So the properties of the DCT transform function are separable, they are separable, they are symmetric, they are symmetric, as well as they satisfy the unitary matrix property, right? So we will go next and talk about the Walsh-Hadamard equation. We in our previous lecture we have seen the Walsh equation as Walsh kernel equation as h of x comma y u comma v is equal to 1 by n into pi I equal to 0 to n minus 1 I power bi of x into b n minus 1 minus I of u. So we have said that capital N is the order of our kernel. Capital N is the order of our kernel, whereas n is given from n. How? Capital N can be represented by 2 power n. So if n equal to capital N is equal to 2, then small n will turn up to be 1. If capital N is equal to 4, then small n will turn up to 2. Right? So what is BI? BI is the ith bit. Ith bit or ith bit in the K in the X representation. Now how X is represented? X is represented by n number of bits. N number of bits. Say if x is equal to 0 and n is equal to 2, like in this condition, n is equal to 2, which implies that x is represented as 0, 0. Right? Now, if I say b naught of x means this is the 0th bit, this is the 0th bit, and this is the first bit. So if I write as b naught of x, then this is the 0th bit that we are referring to. So which is equal to 0 in this case. Say suppose if x is equal to 5, if x is equal to 5 for n equal to 4. Say suppose n equal to 4 and x is equal to 5. So what will the x represented as? X should be represented by 4 bits and the value of 5 should be represented by 4 bits. So we can represent the value of x as 0, 1, 0, 1. So b naught of x here is the 0th bit representation of 5, which is equal to 1. b1 of x is equal to 0, which is the first bit representation of 5, this is 0. So b2 of x is equal to 1, b3 of x is equal to 0, right? So if we observe here, Walsh and Hadamard equations are dependent upon the number of bits, that is small n, and the ith bit representation of x and u values. So it is a non-sinusoidal equation, non-sinusoidal transform function, as well as it is a orthogonal function. This is the 1D function. If we have already seen the 2D function, so if we want to see the 2D function, so 2D function, if we have to write h of x comma y u comma v, we have written it as 1 by square root of into pi of I equal to 0 to n minus 1 bi of x into bn minus 1 minus I of u plus bi of y into b n minus 1 minus I of v, right? So we have seen this equation. We can even say that it is a separable function by dividing it into two 1D functions, which is given by I equal to 0 to n minus 1 bi of x into b n minus I of u into 1 by square root of n into pi I equal to 0 n minus 1 bi of y into b n minus 1 minus I of v, right? So we can write our transform function by separable into two 1D functions. So based on this, if we calculate this matrix 1D function, we can get the total output transform function. So let's continue for the order 2. So if n is equal to 2, which means that small n is equal to 1. Small n equal to 1, which represents that I am going to represent my values x, y, u, v by 1 bit. I am going to represent my x, y, u, v values by 1 bit. Now what are the ranges of x? Is equal to 0, 1, so on n minus 1. So which is equal to x will have the values 0 and 1. Similarly, we have y, u and v values also belong to the range 0, 1. Right? Now, let's calculate the value of Walsh-Hadamard coefficients, which is we are representing it as h of 0, 0. So x is equal to 0, u is equal to 0, and we are representing the values by 1 bit. So we get the value as 1 by square root of capital N into pi I equal to 0 to n minus 1 into minus 1 bi of x into bn minus 1 minus I of u. So here if x is equal to 0, u is equal to 0. So implies that b0 of x is equal to 0, b0 of u is equal to 0. So b1 of x and b1 of u doesn't exist in our case because n is equal to 1, right? So h of 0, 0 is given by 1 by square root of 2 into pi I minus 0 to 1 minus 1 which is 0, when I minus bi of x into bn minus 1 minus I of u, right? So we get the value as 1 by square root of 2 into minus 1 power b naught of 0 of x is 0, b n minus 1 minus I. It is equal to 1 minus 1 minus 0. So the value is equal to 0. So b naught of u is also equal to 0. So we get the value as 1 by square root of 2, right? Now, if we want to calculate the function of h0 comma 1, so if we do that, we can see that the equation turns up to 1 by square root of 2 into minus 1 b naught of x into b naught of u, which will again turn up to be 1 by square root of 2. Similarly, if we calculate h10, we get the value 1 by square root of 2. Whereas when we go for h11, we get the value as 1 by minus 1 by square root of t. So our Walsh equation transform function of order 2, we get the values as 1 by square root of 2, 1 by square root of 2, 1 by square root of 2, minus 1 by square root of 2. So this is our Walsh transform function, which is given by 1 by square root of 2, 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 minus 1 by square root of 2. So this is the procedure how we do. We represent x. We first calculate the order, which is n. From there, capital N, we calculate the value of small n, which is given by n is equal to 2 power small n. So from this equation we get this value of small n. So from this we get to know how many bits x and y are represented by. Then we get to know that x and y values range from 0, 1, so on till n minus 1. So the number of possible combinations that we can have is x 0, 0. For x and u, conditions are 0, 0, 0, 1, 1, 0, 1, 1. So from there we try to calculate h of 0, 0, h of 0, 1, h of 1, 0, and h of 1, 1. So that can be represented in a matrix form by representing W2 is equal to 1 by square root of 2, 1 by square root of 2, 1 by square root of 2, and minus 1 by square root of 2. Right? So now, if I say order n is equal to 4, right? So if order n is equal to 4, which implies small n is equal to 2. Since n 4 can be represented by 2 square, so capital N is equal to 2. So I have values of x, y, u, v ranging which belong to 0 to 3, right? Which is n minus 1. And I have each x, y, u, v represented by 2 bits because my small n is equal to 2, right? Now, I'll have the values, the combinations. Let's write it in the form of a table. So x, u. So I'll have x is equal to 0. Then I have the values combinations as 1, 0, 0, 1, 2, 3. Right? When y is equal, then x is equal to 1. I have the values 0, 1, 2, 3. Then the value of when x is equal to 0, I get the values of 0, 1, 2, 3. Right? Now, when x is equal to 3, I have the values ranging from 0, 1, 2, 3. So, I will get when x is equal to 0, it represents the first row of my Walsh kernel, Walsh transform function, the coefficient matrix. When x is equal to 1, it represents the second row. This becomes the third row, and becomes the fourth row. So from here, we can see that the Walsh transform function is of order 4 cross 4. Right? Let's calculate for the first row. When x is equal to 0, u equal to 0, and we are representing the values by 2 bits. So b naught of x is equal to 0, b1 of x is equal to 0. When u equal to 0, b naught of u is equal to 0. When b1 of u is also equal to 0. When u equal to 1, b naught of u is equal to 1, b1 of u is equal to 0. When u equal to 2, then we get the value of b naught of u as 0, b1 of u as 1. Since 0 by representation of 0 is 0 0 0 1, and 2 can be represented by 1 0. When 3 u is equal to 3, b naught of u is equal to 1, b1 of u is equal to 1. Since 3 can be represented by the value 1 1. So using these combinations, I can calculate my first row of my Walsh kernel. So that will come up to be, that can be given by 1 by square root of n, 1 by square root of n. So let's calculate for 0 0. It will turn up to 1 by square root of 4 into pi of I equal to 0 to 2 minus 1, which is equal to 1, and 1 minus b I of x into bn minus 1 minus I of u. So from there we get 1 by 2 into minus 1 power b naught of x into b n is equal to 2, right? So this will turn up to, when I is equal to 0, this term will come up to n minus 1. So 2 minus 1 minus 0, 2 minus 1 minus 0, so that will turn up to 1. So this will be b1 of u into minus 1 power b1 of x, b1 of x into, now this function will turn up to b2 of u, right? So n is equal to 2 minus 1 minus 1, so this will become b naught of u. So that will turn up to minus 2, 1 by 2 into minus 1, which is equal to 0 0 into minus 1 into 0 and 0. So that will turn up to 1 by 2, right? So similarly, we can calculate for h11, h01, h01, right? So that will turn up to 1 by 2 into pi I equal to 0 to 2 minus 1. So that will turn 1 minus 1 b I of x into bn minus 1 minus I of u, right? So that is equal to 1 by 2 into minus 1 power b naught of x into b n is equal to 2 minus 1 minus I is equal to 0. That will turn up to bi of u into minus 1 into b1 of x into b I of 2 minus 1 minus 1, which is b naught of u. So that will be turning up to 1 by 2 into minus 1 power 0 into minus 1 power 0 into 1. This is 0 into 0. So this is equal to 1 by 2. 1 by 2. So similarly, we can calculate for h110. We can calculate for h10, then h11. Right? So we can calculate similarly my Walsh-Hadamard equation. Now, When we come for Hadamard equation, the same kernel equation what we have seen in Walsh can be represented here again for Hadamard also, but there is a slight difference. So let's see that. So my kernel equation hx comma y uv for my 2D function is represented by 1 by n into pi I equal to 0 to n minus 1 power bi of x into bi of u plus bi of y into bi of v. So in our Walsh, we have seen that my power of 1 is represented by bi of x plus bn minus 1 minus y of u plus bi of y plus bn minus 1 minus y of v. So instead of this n minus 1 minus I am representing by I only. So when we represent it in this form, we call it as Hadamard equation. So we get my Hadamard kernel values. Similarly, we have calculated the order 2 of Walsh Hadamard. We can calculate the same way in Hadamard equation. So we get our Hadamard of order 2 cross 2 as 1 by square root of 2 into 1 1 1 minus 1. So this will be my Hadamard 2 cross 2 kernel matrix. So when we come for 4 by 4, I get the value as this is 2 by 2. So my matrix would be 4 by 4, which is given by 1 1 1 1 1 minus 1 1 minus 1. This is given by 1 1 1 1 1 minus 1. So from this, if you observe that the same 4 cross 4 matrix can be represented by, if I represented my 2 by 2 order kernel as H2, then I can represent my 4 kernel as H2, H2, H2 minus H2, where H2 is equal to 1 1 1 minus 1, where it is multiplied by the scalar 1 by square root. So the Hadamard equations, the kernel functions can be recursively found out from order 2. So similarly, if I want to calculate the Hadamard kernel for 8, then can I simply write it as H4, H4, H4 and minus H4, where my H4 represent my fourth order kernel matrix, which is given by here. Now, how is H4 calculated? Recursively from H2, right? So this is how Walsh and Hadamard equations can be calculated. Now, if say suppose I have a image is of size 1, 2, 3, 4. Then using my Hadamard equation, I can say that my output image transform function is given by 1 by square root of 2 into 1 1 1 minus 1 into 1 2 3 4 and multiplied by my transpose of my Hadamard transfer function, which is given by 1 1 1 minus 1, right? So if I multiply it, I get the function as 1 4. So 1 plus 3, this will turn up to 2 plus 6, this is 1 minus 3, and this is 2 minus 4 into 1 1 1 minus 1. So this I can write it as 4 4 8 minus 2 minus 2 1 1 1 minus 1. So this will turn up to 1 by 2 into 4 plus 8, 4 minus 8 minus 2 minus 2 minus 2 plus 2, right? So the transform function is given by 1 by 2 into 12 minus 4 minus 4 and 0, right? Which we can further simplify it as 6 minus 2 minus 2 0. So this is my Hadamard transformed input image of f is equal to 1 2 3 4. This is my output image. Now if I want to calculate my I want to calculate my output image. I have my output image v. I want to get back my f, so I can write it in the form of v is equal to, we have written it as a is equal to a into a u into a transpose. This is my how we have calculated our v. So from this equation I can write my value, or I can get back my input image u as, so this can be, since A is the unitary matrix, I can write A inverse is equal to A conjugate transpose V into A complicate transpose into transpose. So I get back my U as A conjugate into V into A conjugate. So I can get back my u from by this equation. So the same v I can get from free. I can get back my input image f by using this formula, right? So similarly, if I want to order 4, so n is equal to 4, we can recursively find it by n is equal to 2. So we found it like h4 is equal to h2 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 minus h2, right? Or we can go on, we can continue the traditional method of n is equal to 4, capital N is equal to 2, then we can find out h b naught of 0, b naught of u, and so on and so forth for different combinations of x and u, and we can calculate our h of 4, which can be recursively found from h2 as shown here. So this would be the end of my lecture today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.